Hello, Elizabeth and Miriam, Ellie and Sam. Hope you all are doing well. This is your pre-calculus class for Monday, March 30th. Today I'll be covering lesson 6.2 in your textbook. This week you will have homework per the syllabus. Lesson 6.2, Section A, odds, problems 5 through 75. Section B, odds, problems 19 through 67. We will take a quiz over lesson 6.1, and help will continue to be by phone or virtual meeting. This lesson is all about the trigonometric functions. We are going to define the trigonometric functions in two different contexts. First, we're going to talk about their definitions in right triangles. I believe this will be reviewed to you from your geometry class. So in this case, since we're dealing in right triangles, we're going to define the functions for acute angles. Of course, we're limited to acute angles because in a right triangle, of course, you got one right angle and the other two angles by definition have to be acute, since the sum of the three angles is 180 degrees. The other two angles must both be less than 90 degrees. So the right triangle definitions have this limitation. We're also to define the trigonometric functions in the context of a unit circle. And this is a very powerful visual tool because here we can talk about unlimited angle measurements. So obtuse angles, angles greater than 90 degrees, or even negative angles can all be understood in the unit circle, so we can see how sine, cosine, and tangent work for those other types of angles. So this is, we're going to basically have two parts here. We'll start with the right triangles. And in general, we're going to be speaking about angles with their measurements in degrees. When we're solving triangles and other figures, we prefer using angles in degrees. However, for calculus and for circular trigonometry, we often talk about angles in terms of radians, but we'll get to that in chapter 7. So for now, we're going to focus on triangles and degrees, even though we will, again, talk about the unit circle in this lesson. Okay? So, a right triangle, right? And the right angle is at vertex C. So my hypotenuse, the side opposite the right angle, is lowercase c. Just go ahead and call this A, this B, so this is little a here and little b here. So my two legs, lowercase a, lowercase b, my hypotenuse is length lowercase c. So of course, Pythagoras, a squared plus b squared equals c squared. Again, the sum of the three angles is 180 degrees. So angle A and angle B are both going to be less than 90 degrees. We're going to go ahead and label this angle B as having a measurement of theta. Theta is obviously the Greek letter we use a lot to represent the measure of an angle. There are several different mnemonic devices that you can use to remember the definitions of sine, cosine, and tangent. I think the most popular is probably SO, CA, TOA. So these are just three-letter acronyms for the definitions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So when we talk about the sine of theta, it is going to be the side opposite the angle divided by the hypotenuse. So in this case, this would be B over C. Cosine of theta the adjacent side, in this case A, over the hypotenuse. So this is going to be A over C in this example. And the tangent of theta is the opposite over the adjacent. So in this case, it's going to be B over A. Okay. We could just as easily have chosen angle A if this was labeled gamma for the measurement. I'm sorry, that's alpha. Gamma would be like this. So the sine of gamma would be opposite over hypotenuse would be A over C. Okay? So we can see that in this case, the sine of this angle A is the same thing as the cosine of this angle B here. Okay? So those are the definitions. Again, I need to emphasize that these apply for right triangles. Okay? Now, so if we're trying to solve for angles in a triangle, we have to make sure that we're dealing with right triangles when we use these functions like this. Couple of other points. Number one, these are ratios, right? So it's the ratio of the length of two sides. So it doesn't matter what the units of length are here. Of course, they have to be the same. But the sine, cosine, and tangent are dimensionless numbers. They have no dimensions because the dimensions cancel since I'm taking a length divided by a length. So it's just a ratio with no units. And it completely depends on what the angle is. It doesn't matter how big or how small this right triangle is. The ratios of the sides are going to be the same for whatever angle this is. If this is 30 degrees, then it doesn't matter how small or how big this right triangle is. This is going to be 60 degrees. So you're going to have an infinite number of similar triangles that are 30, 60, 90 triangles, and the ratios of the sides are always going to be the same. So the sine of 30 degrees is a number, right? So it does not depend on the size of the triangle, just on the measure of the angle. So, if we know one of the acute angles in a triangle and one of the sides, we can solve the triangle. For instance, if theta here is equal to 32 degrees, and I know that B is equal to 12, I can solve this triangle by using my trigonometric functions. It's a right triangle. I can use the trigonometric functions straightforwardly in this context. And I can solve the entire triangle because I know this angle, I know this angle, and I know this side. So this is the angle, side case of a triangle. It defines a unique triangle, a single one, and I can solve for the rest of the parts. So for instance, if I wanted to find this other angle here, that's easy, right? I know that the sum of angle A plus 32 degrees plus 90 degrees is going to be equal to 180 degrees. So A plus 122 degrees is going to be 180 degrees. A is going to be equal to 58 degrees. Okay, so we've solved for that angle very quickly, straightforwardly. Now we can find out what the sides are. So I know what both of these angles are. I can use my trigonometric functions with either of these angles to find my unknowns. I know this side over here, they told me this first, I'm just going to go ahead and use this angle and that side to find the other two sides. So I know that if I want to find out what the hypotenuse is, opposite over hypotenuse, I know this measure of this angle, so I can write the sine of 32 degrees is equal to my opposite over hypotenuse. So it's equal to 12 over c. And now I just solve for my unknown c. Multiply both sides by c. Divide both sides by the sine of 32 degrees. Punch 12 divided by the sine of 32 degrees into my calculator, and I get that c is equal to 22.6. Okay, now I got one side left. I'm just going to go ahead and work with what they gave me. So I'm going to say that the tangent of 32 degrees is opposite over adjacent. Over A, right? So in this case, again, I multiply through by A. So A times the tangent of 32 degrees equals 12. Divide through by the tangent of 32 degrees. So I punch 12 divided by the tangent of 32 degrees into my calculator, and you should get 19.2. So again, in the context of a right triangle, if I know one acute angle and one side, I can solve the entire triangle. I can get all three angles and all three sides using my trigonometric functions. Okay? Again, can't emphasize enough, it's got to be a right triangle. However, we can do some things to force things into the context of a right triangle. If we're dealing with an isosceles triangle, which of course is a triangle with two equal sides. So let's say that we have a triangle A, B, C, and I know that side A is equal to 50, and side C is equal to 50, so they're equal. We got two equal sides, it's an isosceles triangle. And I know that this angle is 20 degrees. Well, here I've got a side angle side case for a triangle. So this defines a single triangle that I can solve all the pieces for. And I can make this into a right triangle case by doing a perpendicular bisector. If I bisect this angle here, this is a perpendicular bisector of the base B here. So this cuts this into 10 degrees, 10 degrees. So now I've got another triangle over here with a 10-degree angle, a 50-degree side, but it is a right triangle. So this, and again, it cuts this side in half. So this is B over 2 here and B over 2 here. So if I want to solve the original isosceles triangle, I can do it in pieces this way. So in this case, if I want to find out what well, I can quickly find out what the angles are, right? I know these two angles have got to be equal to each other. 10 degrees plus 90 degrees is 100 degrees, so this angle here has to be 80 degrees. Same deal here, right? So these two angles are both 80 degrees. I mean, we can check that with the original triangle. 20 plus 80 plus 80 is 180 degrees. So now I know all three angles. I know both of these sides. I need to figure out this side B, but I'll figure that out by solving for B over 2. So if I take the opposite over hypotenuse, my sine of 10 degrees is is equal to b over 2 divided by 50. Okay? So 50 times the sine of 10 degrees equals b over 2. So I'll multiply both sides by 2, and 100 times the sine of 10 degrees is equal to b, the total length of the side. Okay, 50 times the sine of 10 degrees would be just this piece of it, which is about 8.68, but 100 times the sine of 10 degrees would be b, which is equal to 17.36 if you punch that into your calculator. So my original isosceles triangle has two sides of 50, a side of 17.36, and then the three angles, 20, 80, and 80. So, again, we can force this into a case where we can use the trigonometric functions to solve it. All right? Now, we can use we've used the trigonometric functions in the context of a right triangle to solve for sides that we don't know. What if there's an angle that we don't know? So in this case, right triangle, I want to find out what theta is. I know that this leg is 3.2 and this leg is 9.4. If I want to find theta, I can use my tangent function, my inverse tangent function. So we use the inverse functions to go back to angles. We use the function tangent to go from an angle to find out what the ratio of the sides is. But in this case, we know the ratio of the sides, or we can calculate it. And to go back to theta, we use the inverse tangent function. So we write it this way: tangent of theta is equal to 3.2 over 9.4, and that ratio is 0.3404. Okay? So the inverse tangent, or tangent to -1, or arctangent, different ways of saying the same thing. So the inverse tangent of 0.3404, punch that in your calculator. You should have a tangent to the -1 button on your calculator, just like you do sine the -1, cosine the -1. Those are the inverse functions. You should get 18.8 degrees, making sure that your calculator is in degree mode, right? We're going to be dealing in degrees with these triangles, so make sure that you keep your calculator in degree mode, okay? So theta is equal to 18.8 degrees. I can now solve this entire triangle, right? I can use the sum of angles to figure out what this angle is, right? 180 minus 108.8 degrees is going to be, what, 71.2 degrees? And then I can figure out what the hypotenuse is over here by using either the sine or the cosine function with this angle here. So, if we don't know an angle, we use the inverse trigonometric functions, okay? All right. So that was probably mostly review from geometry. Hope this all rang a bell with you. So that is the trigonometric functions in the context of right triangles. Let's talk about the unit circle now. So we're going to define the trigonometric functions in the context of a unit circle. So that's a circle of radius 1, that's bad, with a center at 0, 0. Okay, so this is 1, -1, -1, 1. This is an XY coordinate system. So this is the definition of the unit circle. In this case, we're going to look at angle theta as being 0 at the x-axis, and it's positive as we rotate counterclockwise around this circle. So we're going to look at a point P on the perimeter of this circle. This is the angle theta. Again, 0 here at the x-axis. As I rotate this way, theta is positive. If I go back down this way, clockwise, that is the negative direction for the angle measurement. So angle theta, point P, has an xy coordinate in this xy coordinate system. And I form a right triangle here where this length here is my y coordinate for P, and this length here is my x coordinate for P, right? I go over x and I go up y to find my point P. Well, since this is a unit circle, the length of the hypotenuse in this triangle is 1. And since the length of the hypotenuse is 1, the sine of theta is opposite over hypotenuse. Y over 1 is equal to the sine of theta. In the same way, my x-coordinate, the length of this side, this is my adjacent side, so the cosine of theta is adjacent over hypotenuse. So it's x over 1, which is just x. So x is equal to the cosine of theta. So this simple representation here on a unit circle shows us visually how sine and cosine relate to each other as we go from 0 degrees to 90 degrees to 180 degrees, 270, 360, okay? So you can see that at 0 degrees, the length of this side over here is 0. So the sine of 0 degrees is 0. But the cosine of 0 degrees is 1 because it's the full length here. But then as we go to 90, as we go look at sine here, sine is 0 degrees here, but as we increase to 90 degrees, sine goes from 0 to 1. And the cosine goes from 1 to 0. So it's, like I said, it's a powerful tool for visualizing, again, how these trigonometric functions behave as theta changes. Okay? So, we know that the sine of theta is equal to y. Cosine of theta is equal to x. So this point xy here is cosine of theta, sine of theta. Those are the coordinates of my point P. We know that the tangent of theta is equal to opposite over adjacent, so it's y over x, which is the sine of theta divided by the cosine of theta. So here's a trigonometric identity that we can very quickly see from the unit circle. We know that the tangent of theta is equal to the sine of theta divided by the cosine of theta. It's the slope of this line through P, but the important thing is again, this identity. So we know for any angle theta, the tangent of theta is going to always be the sine of theta divided by the cosine of theta. Another identity that we can see here is that this is a right triangle. So this leg squared plus this leg squared equals the hypotenuse squared. So we can write very quickly that the sine squared of theta plus the cosine squared of theta equals 1. So here's another truth for all angles theta. The sine squared plus the cosine squared equals 1. Okay, and we'll talk about a lot more trigonometric identities when we get into chapter 7. But these are a couple of very basic identities that we can quickly see from the unit circle. Okay? Let's focus in on the sine function. So again, if we look at sine, as theta increases, just going to draw kind of a corresponding sine function out here to the right. So as theta increases, I start at 0 and I go up to 1 and I come back down to -1 and I come back to 0. So again, as I rotate around this unit circle, theta goes from 0 degrees to 90 degrees, and it's positive. The positive y direction is this way, so it goes from 0 here to +1, and then it begins to decrease. It comes back down to 0 at 180 degrees here. It rotates on around to 270 degrees. It drops down to -1 down here, +1 up here. So at 270 degrees, I'm at -1, and then at 360 degrees, I'm back to 0 again. And then if I want to continue this going around this circle, again, I can go to bigger and bigger. So I go from 360 degrees to 450 degrees. I go back up to 1. And as I go to 540 degrees, I go back down to 0, 630, I'm at -1, and the sine of 720 degrees is back to 0. So I can go around and around this circle as many times as I want, and the sine goes from 0 to +1 to 0, and then down to -1, and all the negative values in between here, right? And if I go back the other way to negative, so if I go this way, from 0 to -90 degrees, then I go down this way. So this is -90 degrees and back up, and so far this way. So I can, by going around this unit circle, I can see the values of sine of theta for an infinite number of angles. Okay? And we use that to generate the definition of the inverse sine function, which, if you can recall all the way back to chapter 2 of our book, in lesson 2.3, we defined the inverse sine function in the chapter when we were talking about inverse functions. But we can use this unit circle So let's say, again, this is 0, this is 1, so here's 0.5, 1, 2, 3, 4, 5, 6, 7, 8. That's rough, but so let's say that we wanted to solve the equation, the sine of theta equals 0.4. Okay, so here is 1, 2, 3, 4. Here is 0.4 on my y scale, and this is my theta that produces a y value equal to sine of theta equal to 0.4. Okay? The interesting thing is I've got a congruent triangle over here that produces the same y value. So I've got another angle, we'll call this beta, that also produces, well, no, this is another value of theta. That's a little confusing, but it's another value of theta that produces the same value of 0.4 when I plug it in, right? So I can have two, we'll call this theta prime to differentiate them. So I've got 2 points on the unit circle, since, again, this is the positive y direction. I've got 2 points on this unit circle that produce a sine of theta value of 0.4. Now, when we punch the inverse sine of 0.4 into our calculator, we get one answer, right? We get the answer of 23.6 degrees, as long as you're in the degree mode. And that is the one solution here, right? Doesn't give me this other solution. I know that I have another solution. So one solution is theta equals 23.6 degrees. I have another solution, theta equals 180 degrees minus 23.6 degrees, because this angle in here is also 23.6 degrees. So this angle theta prime here is, we'll call it theta prime, is 180 minus 23.6, which is 156.